We've got one final talk for today. So Des Higham from the University of Strathclyde, and he's going to talk about efficiency in multi-level Monte Carlo for large-scale Markov chain simulations.
Thank you. So thank you, Simon. Thank you for the organisers for having me along. My background is in numerical analysis and algorithms and analysing those algorithms. So that's the kind of talk you can expect from me today. In particular, today we're talking about efficiency. So we've heard already, and I think we'll hear many more times this week, about Gillespie-style simulation or continuous time Markov chain simulation. And I want to talk about a few different algorithms for doing that and how to compare the efficiency. If that's an important issue, how do we compare the efficiency of those methods? This is based on some joint work that's, after a long gestation period, finally been submitted. So this is joint with David Anderson, who's here in the audience, and Yu Sun is one of David's PhD students. The work builds on some previous work that we've done together, so there are some more references there that you're welcome to chase up. Today I'm just going to talk about the main ideas. Tomorrow and the next day, I'm sure that Dave will touch on some of these ideas as well, from a maybe more tutorial type perspective. So I'm trying to give you some of the end points, and then if you want to fill in the details, then you'll hear that from Dave Anderson. And also Mike Giles, who's the key developer in multi-level Monte Carlo, is giving a talk on Friday. So there'll be lots of chances to hear different viewpoints on some of these ideas. At the risk of annoying people that know this stuff, here's a very, very simple example trying to summarize the kind of issues that I want to get across. This is a single reaction. We have a species S. All that S can do is disappear. So it's a pure decay process with rate constant 1. You can think of 10 green bottles on the wall and they gradually fall off. That's the kind of example I think of. This is or radioactive decay, if you like. So this is the time axis, starting with 10 molecules. The red dots there give you a sample path from the classic continuous time Markov chain model, or the Gillespie style, or the chemical master equation model. So here we're counting in an integer discrete manner how many molecules there are at time t. All that can happen is a molecule disappears. Under the standard assumptions, that waiting time between events is exponentially distributed, and the expected waiting time is proportional to 1 over the system size. So these red dots show me when my computer has decided to fire the next reaction based on those statistics. So that's one sample path from the continuous time Markov chain model. The blue curve here corresponds to a sample path from the diffusion approximation, or the chemical Langevin equation. So here we're replacing the discrete space Markov chain with a continuous diffusion approximation, or a stochastic differential equation. The reason we might do that is because this is a cheaper thing to simulate. We're now representing the state of the system by a real number at every time t along the path. The dashed curve there is the very simple ODE. That's the reaction rate equation, or the mass action equation. And that's just using a deterministic ODE to represent the concentration of the system. One thing to notice here is that the diffusion approximation gets something wrong completely. It gets the monotone decay wrong. So locally, the diffusion approximation isn't doing a great job in that sense. So that's with 10 molecules at time 0. Let's go to 100. So there's 3 more sample paths of those, one of each of the 3 processes with 100 molecules. And you can see up here where the system state's pretty large, there's not so much discrepancy between these 3. And it's when you get down to where we were before that you start seeing the differences. Okay? So if capital N is the initial number of molecules in the system, then we can think of n going to infinity. That will be called the thermodynamic limit in the physics sense. And in that limit, these 3 processes converge in some sense. In this talk, we're thinking of the continuous time Markov chain, or the Gillespie version, as the exact model, and we're thinking of the diffusion approximation or the mass action ODE as approximations to the exact model. As n goes to infinity, those three things converge to that same deterministic ODE. In terms of closeness, the Langevin equation has an order 1 over n type error, so that's closer to my exact solution than the ODE model. Okay, so that's the sense in which I want to look at these models. So again, a little bit of background for those that aren't familiar with this Gillespie-style simulation. So those discrete, those integer-valued continuous time Markov chain models are incredibly popular now in systems biology, in computational cell biology, but they also arise in many other areas. I've listed a few of them there. We can sample these exactly, so we can compute sample paths of the Markov chain with the exact statistics. Okay, so there's no sense in which we need to approximate that model. We can get hold of exact sample paths, and this was shown in a paper by Gillespie in the 70s. There's also earlier work in other fields where exact sample paths are computed. This has been particularly successful in terms of getting citations and generating interest in the field. Gillespie also showed how the modeling goes through. So in terms of chemical kinetics, he properly justified that continuous time Markov chain model from very basic first principles. In the physics literature, the same idea is sometimes called BKL, and there's an alternative implementation of the Gillespie-style algorithm, the Gibson-Brooke version. So these are all very popular, widely used algorithms or variations of the algorithm. The names that you might come across include Gillespie's algorithm or stochastic simulation, discrete event simulation, next reaction method, and many others. So this computation is nice in the sense that we can do it exactly. There are no discretization errors. On the other hand, it can be expensive. If you want exact sample paths, then you have to take account of every reaction that takes place in the system. And as you can imagine, that can be expensive. And for that reason, alternatives have been proposed which do an approximate job. They approximately give you sample paths from that continuous time Markov chain, or they approximately compute quantities that you want out of that Markov chain model. And I'm going to focus here on a method called tau leaping, which is in a sense an Euler method applied to the Markov chain model, and then that diffusion approximation that I mentioned, the chemical Langevin equation. These are widely used and successful ways to approximate the Gillespie-style simulation process. And I'll point out now what I think is one of the key issues, which I'll return to again later. So we'd like to somehow understand why these approximation methods might be useful. They seem to be successful in practice. Can we quantify that they do a good job? Well, here's an issue which I think needs to be addressed. If you take a fixed problem, so a fixed chemical reaction system, and just ask for more and more accuracy, so what's the cost of achieving higher and higher accuracy when we simulate a fixed system, then trivially those approximation methods will start to look bad, because the exact simulation process will eventually be the cheapest way to do it. Another way of saying that, at least in the tau leaping sense, is that if you discretize with Euler in this tau leaping way, if you let the tau leaping step size tend to 0 on a fixed problem, then eventually you'll be working harder than exact simulation. And let me go back and just try and explain that a bit more. Any of these continuous time Markov chain models ultimately give you piecewise constant paths. Nothing happens in between the reactions. So the exact solution path is piecewise constant. If you discretize that with, say, Euler's method, you're discretizing ultimately constants. So you're wasting effort discretizing things which are not changing. So taking a fixed problem looking at the tau leaping parameter going to 0 ultimately is not worthwhile, in the sense that what you're looking at is arbitrarily more expensive than the exact simulation. Okay, so that's one issue to keep in mind. On the other hand, we want to look at the case where the computation is expensive, because that's where these approximation methods are worthwhile. So let's think of the system size going to infinity. So we have a larger and larger problem to solve. Well, in that case, ultimately we get the reaction rate equation, the simple deterministic ODE. So in that well-defined limit, the problem in a sense becomes much easier. We can just use a deterministic ODE solving method. So thinking about that limit, the fluctuations disappear. Essentially, the system size parameter disappears, and we just solve a simple ODE. So neither of these two limits by themselves, I think, are appropriate for analyzing and comparing methods. So we're going to do something different, and I'll show you one particular way to judge the complexity of these methods. The other aim of this talk is to look at multi-level versions of Monte Carlo simulation, and try to get some way to judge the efficiency of multi-level. Okay, so there's a little bit of a skip now into the diffusion process, or the stochastic differential equation model. This is where the multi-level idea was first proposed by Mike Giles. Everything that's coloured here and capital is random, or a stochastic process. So at the top there, I've written down a stochastic differential equation driven by Brownian motion. Think of it as a scalar, but these ideas also work for systems. So we're given a fixed time interval, and we're given the initial condition. We can approximate that by discretizing, and the standard method is Euler-Maruyama. So here I've got a step size h in my method. The delta w's are the increments of the Brownian path, so those are generated from a Gaussian random number generator. It's a discrete time approximation. The time points are multiples of the step size, and I'm going as far as the final time point. Now in this talk, I'm focusing on the case where we're looking for an expected value. That's the quantity of interest. To keep it simple here, it's the expected value of the solution at the final time point. More generally, most of the numbers that you want out of a simulation can be regarded as expected values. So the obvious way to get that expected value of the final time solution value is to compute lots of paths with your discretization method, and then take a sample average. So this number mu here is just a basic sample average over a large number, capital N, of Euler-Maruyama paths. This is then my approximation to the true expected value, and we can break that down into these two parts. This is the classical way to analyze the error in this weak sense, just using linearity of the expected value operation. The reason this is useful is because this splits up the error into two well-defined terms. The first expected value there is just looking at my numerical solution and comparing it with the exact solution in expected value. So that's something we can analyze using standard numerical analysis. That's the weak error in my method. That's known to be order h, where h is the step size. And the second term here, this difference between the numerical method's average and the computed average, the sample average, that's just the statistical error. That's non-zero because we're taking a finite number of samples. So we can look at those two terms separately. For the whole of this talk, there's going to be a parameter, epsilon, which is the accuracy requirement. So I'm assuming that we're given epsilon. Our task is to compute this expected value to an accuracy of order epsilon, and by that I mean in the sense of confidence intervals. So we need a confidence interval of width order epsilon in our computation. So to get the confidence interval down to that level, both of these terms have to be order epsilon. So the standard thing to do is to choose your step size so that the bias or the weak error is order epsilon, and choose the number of samples so that that statistical error also matches order epsilon. That tells you what kind of method you need. If you then work out the complexity, and this is measured, for example, in terms of the number of random numbers that you generate, or the number of times you evaluate the right-hand side, the A and the B. So the complexity of achieving order epsilon accuracy is the order of epsilon to the -3 if you do it that way, so with the standard scaling. And for example, if you look in books on mathematical finance for option pricing, this is the complexity that they quote for applying Monte Carlo to an SDE to price financial instruments. That seemed to be regarded as the cost of Monte Carlo in this discretization of SDE setting. But then Mike Giles came along and in 2008 showed there was a different way of doing it. And this reduces the complexity effectively down to order epsilon to the -2. So if you want 2 digits accuracy, this can be 100 times quicker, this new way of doing a multi-level version of Monte Carlo. It doesn't exploit anything about the structure of the SDE. It's completely general, and you do see these improvements in practice. So it's easy to achieve that kind of speed up. So it is, in my opinion, a fantastic idea that is revolutionizing, at least in the SDE setting, the way that Monte Carlo is done. There's not time to go through all the details, but I'll try and give you some insight, and you can learn more as the week progresses about multi-level, for those that haven't seen it before. So one of the key ideas is that you don't simply apply Euler-Maruyama with one choice of step size. So you apply it multiple times with different choices of step size. So there's a range of different step sizes we're prepared to use here. So my notation now is that the subscript is telling me which step size I've used to approximate the final time value of the SDE. So let's take this expected value here. That's the expected value of my discretization at the smallest step size. I can trivially expand that by adding and subtracting the Euler-Maruyama solution at the next coarsest step size. So you may think of this as using a control variate. My control variate is my solution on a coarser grid. Then we can keep doing this. We can expand that coarser solution in terms of an even coarser step size, and we can go down right to the end. So we can then have a combination of expected values. This is a trivial identity. It's a telescoping series. Most of the terms cancel, and you're left with the left-hand side. And there's no reason why this should work. It just happens to work that if you estimate that right-hand side appropriately, it's cheaper than estimating the left-hand side directly. You can make the variances by coupling these two together appropriately. The variances are sufficiently small that there's a benefit in simulating that right-hand side. And you'll see the details, I think, either tomorrow or the day after, if you're interested in that. This little picture tries to summarize what you do in practice. This is in the case where those step size levels differ by a factor of 2. So my refined grid here has a step size hi, and my coarse grid has a step size that's twice hi. You can imagine some underlying exact path of the SDE. That's given by the solid curve. The red asterisks are my Euler-Maruyama path computed on the refined grid, and then the blue circles are the corresponding Euler-Maruyama path on the coarser grid. So it's the same underlying Brownian path, so the same Brownian increments, but 2 different step sizes. Because they're using the same increments, they're very tightly coupled, and the asterisk and the circle stay together at the end of the path. And it's that coupling between those 2 paths that is used in the analysis to show that this is a worthwhile computation. I'm not going to go through the details, but there's one particular step that I felt was worth pointing out, because this is what's going to change in the work that I'm going to talk about. So the paper by Mike Giles, he first of all proposes this idea, and then he analyzes it to show that it's worthwhile. The analysis includes an exploitation of the fact that Euler-Maruyama is strongly convergent. So before, if I go back, if you're just computing with standard Monte Carlo, you just need to know about the weak convergence, whether you're getting the correct expected value with your method. The way that Mike Giles analyzed the multi-level version, you had to also exploit strong convergence. You had to know that numerical solution paths were close to exact SGE paths. And here's roughly why that's the case. He used this sequence of arguments. So we're trying to show ultimately that these pairs of paths, coarse and refined, stay close together in the sense that their variance is small. So starting at the top here, Euler-Maruyama on appropriate SDEs, in particular if you have global Lipschitz conditions, then you can make this statement, is strongly convergent, so paths stay close together. Sorry, paths of Euler-Maruyama stay close to exact solution paths. So both the coarse and the refined paths are close to a true path. There's a triangle inequality then that says if they're both close to something, they must be close to each other. So then your coarse and refined paths stay close together, and then you can show that that difference has a small variance. So that's the logic that goes on in one part of the analysis. The reason I'm pulling that out is because that's the step that doesn't work in the context that I'm talking about today. So in the SDE case, that gives you optimal rates of convergence. In the case of small noise SDEs or jump processes, continuous time Markov chains, then you can't simply use these arguments. You have to work a little bit harder. Okay? So that was a little bit on diffusion processes or SDEs. I'm moving on now, or moving back to this Gillespie setting of continuous time Markov chains. This is what I'm thinking of as the exact model that we're trying to approximate. And we're going to use the Kurtz representation, the random change of time representation. So this is not necessarily the one that you're used to when you're thinking of Gillespie. So here's a simple example to try and set it up. So one equation or one reaction, A plus B goes to C. There are three species, A, B, and C. So we can introduce an integer valued state vector which counts how many A, how many B, how many C molecules there are at each time t. And trivially, the number of each at time t is the number at time 0 plus the number of reactions that have taken place times this vector. Because this vector is taking away an A, it's taking away a B, and it's adding a C. So each reaction has the effect of adding one more of those vectors to the state. So R of t counts how many times the reaction has fired, and all the modeling that goes into this then is built into this counting function R. Okay? How many reactions have taken place up to time t, and the standard chemical master equation type of propensity function would lead you to this conclusion, that R of t is a unit rate Poisson process, Y, with this internal clock. This is the rate at which the parameter inside the Poisson process is changing. And it's given by the propensity function, the classic propensity function for this reaction, integrated appropriately. Okay, so this is equivalent to the usual Gillespie style or chemical master equation style formulation. That's the case for one single reaction, and of course it generalizes. So here's a quick overview of the general case, this random time change formulation. If you have D species and each reaction has this type of form, there's a certain combination of species gets converted to some other combination of species. So that's defined through this reaction vector. And each reaction has an intensity or propensity function. We're going to call that lambda k for the kth reaction. Then this representation that Kurtz introduced has this form. There are now k reactions, and each reaction has its own Poisson process. So the YKs are independent unit rate Poisson processes, and then each one has its own time-dependent parameter, and this is where the propensity functions come in. So they come in through an integral inside the Poisson process. Okay, so that's a generalization of the example on the previous slide. It's not only a nice way to write the system, it also gives you a good way to think about simulating and approximating that pathwise. So we can look at Gillespie's tau leaping algorithm from this perspective. So here's a reminder of what the exact process is doing. This is from time 0 to time h, so thinking of discretizing what happens over a single step. So that's the exact version of the process. We can think of an Euler-style approximation, or in a sense replacing that integral by a single Riemann sum approximation with just one rectangle. So use the left-hand version, the left-hand value of the integrand, and multiply by the width of on the base of the integral. So that's going to give us our approximation process, which I'm calling Z. So rather than the exact integral, I'm now doing something discrete. I'm taking the left-hand value of the integrand times the length of the integral. And remember, these are unit rate Poisson processes. This gives me an algorithm which is essentially taking k samples from independent Poisson processes and using those k samples to update my system. This is what Gillespie proposed. It's a very neat idea. It avoids the issue of having to take account of every single reaction that takes place over that time period. You're essentially freezing the system at the beginning of the time period and getting some estimate of how many times each reaction will have fired without precisely updating the system in between each. So it's a way of freezing and discretizing along the path. In what we're doing, we're going to need a continuous time approximation. So if I go back again, I'm going to take this discrete valued process Z and interpolate it into a continuous time process in the obvious way. So we're introducing here continuous time, but I'm just composing here with a step function. So eta just tells me which step I'm in. So I think this is the best way to think about it. Eta takes the value at the left hand of whichever interval it's in. So if you're in the interval from Tn to Tn plus 1, then eta of s just takes the left-hand value Tn. So I'm just making this into a continuous time representation along the path. That allows us then to use some of the tools of stochastic analysis that apply to continuous time processes. Well, that was tau leaping summarized briefly. I mentioned that in the diffusion case, the stochastic differential equation case, that Mike Giles has this multi-level version of Monte Carlo, which dramatically improves the computational complexity. And with Dave Anderson, we looked for a corresponding multi-level version of this tau leaping process. The key difference here is that it's not Brownian motion that's driving the randomness. It's now sampling from Poisson processes that has to be done. So it's a different type of distribution. It's discrete value, it's jump process driven. To motivate what we did, here's a little example. We're trying to get pairs of paths with different refinement levels which are closely coupled together. So here's a simpler version of that question. Suppose you want a pair of Poisson processes with particular intensities, say 13.1 and 13. How would you generate those to make them tightly coupled? Well, here's what you don't do. You wouldn't simply take a pair of independent Poisson processes at unit rate and put in 13.1t for the first one to give one process, and then in the other independent process put 13t for the other. So completely independent Poissons running at the appropriate rates. The variance of the difference between those, because they're independent, is simply the sum of the variances. So these are not tightly coupled in that sense. What you should be doing is taking these two to be as close as they can be together, so let them both start off with the same process, y1, at rate 13t, and then perturb one of them as necessary to make sure it has the appropriate rate. So if you think of these two processes, they're mostly jumping at the same time, and then occasionally this one has an extra jump. So most of the time they're doing the same thing together, and occasionally one is allowed to do a little bit more. And trivially, the difference between them is just this extra bit we added in, so that's a variance of 0.1t between the difference. So that's the insight into how we couple together different levels of discretization when we're simulating in the tau leaping sense. More generally, in that tau leaping algorithm, we have general non-homogeneous Poisson processes, say with two different intensities that we're trying to couple. So we now need to have three different unit rate independent Poisson processes. We make them share as much as they can, so we take the minimum between these two intensities, and then we add in what's necessary. These are two independent Poissons which add in the appropriate corrections to give them the right rates. Okay? So they share as much as they can, and then we add in the corrections to get the statistics right. It may look a little bit complicated, but it's actually straightforward to make this happen. It's very similar to standard implementation of tau leaping. So that's one difference. We're using Poissons rather than Brownian increments. Another key difference in this setting is that we do have access to the exact process. So in the SDE setting, you have these different levels, and you go down as far as the most refined step size you're prepared to use. In this case, we can go down as far as the exact process. So we can couple the exact process to a tau leaped process and then use tau leaping with different step sizes as far as we like. The consequence of that is that we can do unbiased Monte Carlo in this multi-level setting. Okay, that telescoping series collapses to the correct expected value. So we can do unbiased multi-level Monte Carlo in this tau leaping setting. So in the original work with Dave, we did analyze the performance of this algorithm. What we'd like to do now is to have some system where we can compare different algorithms. Okay? Just to emphasize, I'm regarding the continuous time Markov chain as my exact model. I'm looking at these various approximation methods and or exact simulation. I'm looking at standard Monte Carlo and or multi-level Monte Carlo. So there's a lot of choices there to compare, and it's not clear a priori which method is best or under what circumstance one of those methods may be best. We're going to focus on the case of classical scaling. So under mass action kinetics, there's a classical scaling of the system size represents volume times Avogadro's number. So that's the version that we're going to use. So we'd like to think of large system size, n goes to infinity in this scaling. As I mentioned earlier, we've got to think carefully about limits. If we fix the problem and let h go to 0, then ultimately tau leaping works harder than exact simulation. So that's not a sensible thing to analyze. If you let the system size go to infinity by itself, the problem becomes deterministic, and again, that's not sensible to analyze because you can just solve the ODE and get the solution. The motivation for what I'm going to say comes from this earlier paper, which just looked at tau leaping, where they were fully aware of this issue, and they looked at this coupled limit. So they're looking at strong and weak error in tau leaping in this regime where they let the step size go to 0 and the system size go to infinity. So they couple those two together, so they have some parameter beta, and they let h be n to the power minus beta. So it's an increasing system size and a decreasing step size. In that setting, the fluctuations remain important because you have to take smaller and smaller step sizes to keep track of those fluctuations in a bigger and bigger system. So that's at least a sensible thing to look at. We're going to copy that idea in this slightly more general setting where we want to compare exact simulation as well. So we're going to analyze these methods in the setting where the accuracy requirement, epsilon, that's the confidence interval size, is coupled to the system size. So there's some positive parameter alpha that we're given that tells us how much accuracy is required. So it tells us the relationship between the accuracy requirement and the system size. Okay, so it's important that we remember that relationship. The error requirement is some negative power of the system size. So we can now look at the limit epsilon goes to 0 and equivalently n goes to infinity. So we're looking at harder and harder problems and asking for more and more accuracy. That's one way to think about it. So there's a reminder of the relationship. But it's important to keep in mind that this is no longer a single problem that we're solving. We're looking at a parameterized family of Markov chains parameterized by this n, the system size n. So it's not a fixed problem, it's a family of problems that we're looking at. In this setting, there's no real reason to consider alpha equal to or below a half, because if alpha is chosen in that range, then the fluctuations really aren't important. You can solve the deterministic reaction rate equation and achieve the required accuracy. So we're not going to think about alpha less or equal to a half, because the answer then is trivially solve the reaction rate ODE. Okay? So that if alpha is less or equal to a half, we're saying we don't care about the fluctuations, in a sense. Okay? And just to make it clear, when we talk about the diffusion approximation with this classical scaling, we have to be aware that the SDE has a small noise term. So this is the one way of writing the chemical Langevin equation with this scaling. So there's a 1 over root n factor in the diffusion term in the SDE. So as part of the analysis that goes into the results I'm showing, we had to analyze multi-level Monte Carlo on SDEs with small noise, which turns out to be different to standard SDEs. To get the optimal rates out of it, we have to analyze small noise SDEs separately. So we're now in a position to think about comparing accuracy. So there's a whole load of analysis which I'm sparing you. I'm going to give you the table of results, which we've sweated over for a couple of years. We can now compare the exact simulation with various types of discretization, including tau leaping and multi-level variance. Just to emphasize, this is a parameterized problem, so the variances, or the variance of the target we're looking for depends on n. So we have to keep that in mind when we do the analysis. But I'm going to show you the table of results. There's quite a lot to take in. These are the methods that we analyzed. This is the cost of applying the method to achieve accuracy epsilon. We've written it in terms of n under this scaling. So n goes to infinity. What we really have here are upper bounds on the cost. We've shown that you can do it with this cost. But we've also done some very detailed computations. So as far as we can tell, these bounds are sharp. So we believe these are the costs of the methods in this regime. So this is Monte Carlo with exact simulation, or Gillespie. Monte Carlo with tau leaping, with the appropriate choice of step size to get the bias right. There's a midpoint version of tau leaping, which has higher accuracy in that h goes to 0 sense. This is Monte Carlo using Euler on the diffusion approximation, or the SDE. This is multi-level Monte Carlo on the SDE with Euler. This is the multi-level Monte Carlo version of tau leaping. This is a biased version, and this is an unbiased version of multi-level Monte Carlo with tau leaping. So the unbiased version uses exact simulation at the most refined level, so that we have no bias in the estimate. So this depends on alpha. Alpha is telling us how much accuracy we're asking for relative to system size. So larger alpha means we're asking for more accuracy. So we're asking the algorithm to work harder. In this column here, we've pointed out which of these methods is best, or at least joint best, in which parameter regime. So there are 4 algorithms which either win or jointly win for various parameter regimes. But looking at the first 3 rows, one thing we can do here is quantify the benefit of tau leaping. So there is a regime where the tau leaping cost is cheaper than exact simulation. That happens if alpha is not too big. It's alpha up to 1 in the standard case and alpha up to 2 in the midpoints, the higher accuracy tau leaping case. So if you don't ask for too much accuracy, then tau leaping is beneficial. That makes intuitive sense. If you want too much accuracy, then tau leaping no longer becomes valid. You may as well solve the exact problem because the step size is so tiny that you're discretizing things where nothing changes. But looking at more generally at the results here, multi-level generally wins out. In particular, multi-level on the SDE is looking good. However, what we're glossing over here is the fact that the SDE itself is non-linear. We're assuming the standard behavior of numerical methods on SDEs. If I go back and show you, there's actually a square root sign here. So this is a non-linear diffusion coefficient. So the results that we're using don't really apply to this type of non-linear problem. There are also issues with the solution going negative. So we're being as generous as we can when we analyze the SDE setting. For the tau leaping computations, we don't have that issue of wondering whether the solution is converging, the numerical solution. Okay? So looking at the cost here, maybe there's a bit too much to take in, but it turns out that multi-level does better for a wide range of parameter values. And I've said here, the SDE approximation has issues with both the convergence and the non-negativity of the computations. Okay? So there's a well-defined sense in this particular regime where we can analyze computational time and specify which of these methods works best. Just to summarize what I've talked about there, the motivation for this was to try and compare methods. There's a lot of literature where methods have been tried on particular examples, where analysis has been done, but we feel that there was a need to clarify when and where a particular method is useful. We've chosen this regime where the accuracy that you ask for scales with the system size because we think that's an appropriate way of measuring complexity. With the results that we got, in one sense, suggest that the diffusion approximation is worthwhile. You can achieve at least the best, and in some cases the uniquely best order of complexity through the SDE setting. To do that, we had to make sure that we took account of that small noise structure in the SDE, otherwise the estimates are not optimal. But on the other hand, we're pulling out strong convergence theory for the SDE simulation, which may or may not work in this nonlinear setting. Also, another point to mention is that the SDE version is biased. So we're achieving the right accuracy in the sense of order, but we don't know what the constant is in front of that order of bias. So there's no way of guaranteeing without a lot of extra work that confidence interval is around the appropriate point. Okay, the confidence interval applies to your numerical approximation, not the exact expected value, whereas this multi-level version can be made to be unbiased. Okay, so it's the appropriate confidence interval that you're getting. Okay. So in summary, our method of choice is the unbiased multi-level Monte Carlo version of tau leaping in this setting. Just to emphasize, this is looking at general reactions, so we're not making any specific assumptions about the types of reaction that we're analyzing. This is general in the same way that Mike Giles' original work was general. And it applies in the case where we did the classical mass action scaling to the system. There are many other possibilities, and in particular, I'm sorry, my last word has a typing error, it's always the case. There are many other structures you could think of where you have multi-scale effects in a system, and you could then do appropriately customized algorithms and then also do the corresponding analysis on those. Okay, so I'll finish there. Thanks for your attention.
Okay, so has anybody got any questions? Peter?
So when you listed the sort of the conceptual outline for the multi-level Monte Carlo for SDEs, you said this doesn't work for continuous time Markov chains. I understand you have to do, of course, technical innovations to get the idea to work for continuous time Markov chains. But was there something conceptually about those basic steps that don't carry over to continuous time Markov chains? I missed that point.
Maybe we spent it took us a long time to think of it. That's probably one answer. Maybe Dave's got more insight.
So your question is what conceptually?
Just conceptually, I mean, I understand that making it work, it requires non-trivial development. I'm just saying, is there anything conceptually about the outline that was fundamentally not?
Yeah, so they studied the L2 error and then used the L2 error as an upper bound for the variance, and that just works perfectly. It's a sharp upper bound for the variance. And what we had to discover is that doesn't work for us. The L2 error, because of the Poisson processes, is not a good estimate for the variance. And so you have to estimate the variances of the differences directly, which is much harder, right? Because it's the L2 minus a term, so you get the negative term. You can't just upper bound away. So you have to be really delicate. So is that what you're asking
I don't know.
about?
I sort of understood from you that something about strong convergence was essential for the SDE approach, but you do have a strong convergence in the continuous time Markov chain case too.
Yeah, but the strong convergence is typically given as an L2, right? So you look at how the L2 difference goes to zero.
Okay.
That is not a sharp. Well, you don't care about the strong convergence for MLMC. You care about the variance between the paths. And so if it's sharp, you're happy. Otherwise, you have to estimate the variance.
Sorry, I was thinking the question meant about the coupling. How did we find that coupling? That was.
No, I mean, I understand what you had to do and all that. I was wondering if I missed that there was something. I'm not trying to downplay anything. I'm just saying I thought you said something that I missed when I read your paper the first time.
Yeah. Well, yeah, we just looked at lots of. Actually, it was more or less in Kurtz's work how to couple, but we took a long time to find. He was using it theoretically, and we realized you could use it algorithmically.
So I understood that you use the sample variance to estimate, the variance to measure the error.
Yeah.
You did not face the large cortices problem, so you have this kind of, when you make many simulations, not all the simulations are, useful for estimating the variance.
Right.
So, because we are working on this type of problems, and when we use the sample variance, we face this kind of problem. How you treat it,
Yeah. Well, in terms of solving that nonlinear SDE, there are some really nice pieces of work about really how to get over the fact that some paths can blow up. And if you throw those paths away, under certain assumptions, you still get the right answer, if that's what you mean. So if you're solving the diffusion approximation, you can essentially get rid of the bad paths and still do something sensible, or the ones that go negative, for example. Is that what you were meaning?
Yes.
Yeah.
Your cost analysis looks only at scaling with large n. What about for smaller n? I mean, there's some sort of trade-off where one is excellent at huge system sizes, which actually takes a huge size before it actually gets worthwhile.
Yep, exactly. So we're really trying to back up some of the computational experience that's been published. We only analyze n goes to infinity. You could argue that for small n that's easy, but I agree there's some intermediate states. A bit like Kostas was saying, there's always some intermediate state where things cross over, but I've got no feel for how you might quantify that.
Some sort of advice in terms of which methods to use for average size n, or in terms of one of these things look excellent this analysis, but actually it's not that good and turns out because of this scaling factor?
I would just say do exact simulation until it's killing you, and then think about making it better. That's probably the best advice.
Have you tried to experiment with this trick by Glynn, where you randomize multi-level and then you get unbiased estimator for SDs because you have a small noise regime, so you have optimality on the variance?
No, we haven't tried that. So it seems like it's almost too good to be true, but then so did Giles's work, so that is something worth trying. Yeah. There's a way to make SDE multi-level unbiased. That seems really neat. Yeah.
I was wondering how you choose your finest scale for the tau leaping, because in the SDE setting, you basically pick your finest level to be the one that you can handle to compute.
Yeah.
But here, you don't want to do that because that might not necessarily be a sensible thing to do. So how do you choose that finest level?
In this setting, we have the work by Anderson and Kurtz and others, which told us how the bias operates. So in the analysis, we know how to do that to the right order of accuracy. In practice, you have to just experiment, work out variances.
Okay, so if you've got any more questions for Des, maybe you can go and speak to him later on. We've now got the poster session. Sorry, we're running 5 minutes or so late. If everybody could make their way to the poster session, if you're a poster person, could you make sure that you're stood nearby so that people can ask questions about your poster? Okay, excellent.